8 and 9 are the last two tutorials in the electricity and magnetism. And then you may think that these contents in the 8 and the 9 are not very important because they are not covered in the quiz 2. But unfortunately, it's not true. This tutorial 8 and 9 actually covered the essence of the electricity and the magnetism. So, well, although they are not included in your quiz, but it's still very important for you to understand the concepts, alright, which are covered in the tutorial 8 and 9. And that's the reason why I will spend a bit more time for to touch those concepts in this week and next week. So we will start with this magnetic field. Alright, so magnetic field is related to the current as well as the motion of the charge particle. Okay, motion of the charge particle. So the magnetic field is related to the moving charge. Okay, moving charge is the presence of the magnetic field. All right, and then as this equation can be compared to the electric force. So electric force is the charge times its electric field, isn't it? So if you compare two equations, you can see the difference. First of all, this velocity, okay, is actually inside this equation. In other words, we are considering a moving charge, okay, a charge in a motion. All right, so electric force is related to the charge in a motion. Okay, then what is the very good example? One of the obvious example of moving charge? Can you give me one example of a moving charge? In your what, small electric circuit. So you have the voltage here, you have potential, resistance, and you also have. So what would be the obvious example of a moving charge? In your circuit, you have the moving charge here, and what is called? Current here. So the obvious example, okay, is of this moving charge is the current. So that's why when there is a current, it's related to the magnetic force. Okay. So we use this right hand rule, okay, to do this this cross product of the vectors. And then I know that some of you actually learned left hand rule, okay, but I will insist this right hand rule in the tutorial class because to be consist to your lecture slide and the lecture video. Okay, so if you are very confident, about your left hand rule, then I'm not going to stop you, okay, from using your left hand rule. But if you still not very sure, then I would maybe try to encourage you to use the right hand rule. Okay, so when the right hand rule states that the C vector equals A cross B. Okay, C equals A cross B. So it's better to memorize. C equals A cross B. So from top to the bottom, okay, C equals A cross B. CAB, okay, CAB. And then this sequence will be followed for our magnetic force together, magnetic force as well. F equals velocity cross magnetic field, okay? F equals B cross D, okay? F, B, E, alright? And then because it's a vector cross, so we have the sign vector. Alright, which is the angle between A vector and B vector.
So he don't see a point from it. So he's doing the signal schools now.
Alright.
Was in
So
school like
now let's practice this right hand rule. So let's
Then
look
when you
at this
scolding me,
diagram.
you go what, buy laptop, is it?
And then the magnetic field direction is given in the diagram. Okay, it's actually pointing into the page. Okay, into the page. So I'm going to use our right hand rule. Well, let's try together. Okay, let's practice this right hand rule. So my magnetic field, okay, going into the page. All right, and then I'm not going to align my index finger to the velocity like this. Then my force is pointing towards the center. Okay? My force pointing towards the center. So the force is acting on this moving charge. Then what will happen to this moving charge? The force is acting on this moving charge. So in other words, this force actually pushing this moving charge. Yeah? So what will happen? This will change its direction. Does it make sense? Okay, now let's practice this one more time on this chart. So I'm going to, so our magnetic field going into the page, alright? And then the speed, the velocity going into this direction, alright? Therefore, my force, again, pointing toward the center. So this is the force acting on this moving charge. So what will happen to this moving charge? The force will push this, yeah, into this direction. So it's going to change its direction again. So in the end, we are going to have this circular motion, yeah, circular motion over the charge when this moving charge is present in a constant magnetic field. Okay, so when this magnetic field is constant, and then the velocity is defined in the paper in this the same plane, then this will going to make this circular motion. Okay? So now, well, now we have some understanding about this circular motion in the presence of the magnetic field. And then this magnetic force is actually acting towards the center, isn't it? So this is actually the centrifugal force. So our magnetic field is actually centrifugal force. In other words, you can actually set the equation as this. So force, which is the magnetic force, which is QVG equals this mv squared over r. Right? And then from there, you can actually derive this equation. Okay, for the radius of this circular motion. Yeah, radius of circular motion. And then we also know that this temporal period, okay, temporal period, which means how many rotations, okay, how fast is this rotation, okay? So this is going to define as 2 pi r, which is the circumference over the velocity, all right? Then, well, we are going to substitute this equation, which was the previous equation, into here, then you will find this equation. Okay, so temporal period is going to be expressed in terms of the charge and the magnetic field now, right? And then, what is the frequency? Frequency is the inverse of the temporal period, isn't it? So this is going to be the inverse of temporal period, and then again, when you substitute this into this equation, you are going to find the inverse of this. Alright? So now we are equipping a few equations and understand this to determine the radius of the circular motion as well as the frequency and then period. Alright? Now this is a bit more complicated case. Now let's assume that this magnetic field is now along the x-axis, and then our charged particle is injected to this magnetic field, right? So previously, now previous diagram, our velocity, okay, has only 2 components inside this plane. Okay, let's say this plane is xy plane, then this velocity has only x component and y component. Okay, which is inside the plane, right? Now, while this velocity now has more than x and y component, it has now z component too. okay, x, y, z component, then what would happen to this motion? Alright, so it's not very difficult to analyze this. First of all, we know that the velocity of this charged particle, okay, which is in the yz plane, in the yz plane, okay, make this charged particle rotate in a circular motion. Yeah, we learned about this in the previous diagram. So this moving particle is going to rotate in the yz plane. Okay, in the yz plane. Then, what would be the contribution of its x component, which is along this magnetic field? So we just need to analyze this x component only. So when from this diagram we know that our velocity is going to have vx I hat, vy j hat, vz k hat. Yeah? And then we don't worry about this y and z component because we already know that those two components will make this charged particle rotate in the y plane. Okay? Now our only combine this component, this x component, alright? So we are going to find what will happen to this x component, alright? So when from our this magnetic force equation, the magnetic force equation says that V equals to this velocity plus magnetic field, alright? And then this now becomes for the x component, okay? Vx I hat plus the magnetic field is also along this x-axis, so I'm going to say that this is going to be V times I hat. Okay, so what is this I hat plus I hat? So if you cross the same vector, what's the answer? What's the result? Yeah, I times sine vector. Yeah, what's the angle between those two parallel vectors? What's the angle of the two parallel vectors? The angle of the two parallel vectors? 0, yeah? 0. So your vector cross product is going to 0. So in other words, this is 0. So there is no force, okay? There is no force acting on the x-axis. So in other words, this x component is not going to be, so this speed along the x-axis is not going to be accelerated or decelerated. This Vx, this x component or the speed along the x-axis is going to be constant, okay? So in other words, this charged particle will move at the same speed along the x-axis. Alright, so now we have two motions. The first motion is this circular rotation on the yz plane, and another motion is just constant traveling, okay, along the axis. So when you combine those two, this is going to be this helical motion. Does it make sense? Yeah? Does it make sense? Yeah? So it's going to move helical motion like this, alright? And then if you want to make one step further, then you can also determine this rotation direction of this helical motion. Yeah. So you can analyze that this velocity in the yz plane is going into this direction. Therefore, if you look at from this direction, okay, from the positive axis, when this helical motion approaching me, this is going to be circular motion, the clockwise, okay, clockwise rotation. However, if you watch this helical motion from the origin, okay, then where this particle actually moves away from me, then this is going to be the anti-clockwise, yeah? So we now have a better idea about this the helical motion, okay? Now, yeah, so we we know that if there's a magnetic field, then there will be this magnetic force. Okay, that will generate a magnetic force. And then now let's assume that we have electric field together. So in that certain area, we have electric field and a magnetic field. Okay, and then the charge is in motion. Then suddenly this will trigger the magnetic force as well as electric force. And then the total force is going to be simply adding up of those electric force and the magnetic force. Okay, and then this is called the electric force. And then I told you earlier that the very obvious example of this charging of the moving charge is actually current. So we now start from this equation, all right? And then this dq is going to be converted to this IDT. Again, using this relationship. So your current is a charge change over the time, yeah? Then this you will end up with this equation, which is the total the magnetic force. Okay, magnetic force is going to be your current times your the length vector towards the magnetic field. All right, vector. So then what is our L vector? This L vector is our length vector again, and then its magnitude is actually the length of the wire, and then its direction follows the current direction. Okay, the current direction. So you follow the current direction. Right? Not the electric direction. Okay, the current direction.
Thank you.
So I just explained about this L, and then what would happen if we are given this curved wire where we will use our very standard strategy here. We are going to break a very small piece, and then we will find this magnetic force contributed by this small piece, and then we will do this integration. Yeah. So I have a small question for you. Which force satisfies the following statement? The force exerted on a negatively charged object is opposite in the direction to the force on the positive charge. So will it be true for electric force or magnetic force or both of them or neither of them? So that's one next talk, yeah. So what will be the answer? Well, you can be wrong, yeah, in the part where we adhere to work. So what do you think? What will be the correct answer? Yeah, we both now, yeah. So what is the correct answer? Like A, B, C, or D?
C.
Uh-huh. I want to shine. Okay. What do you think? Well, it can be wrong, yeah? So this is not a problem, yeah? So what's the answer? What do you think? That's can be your fault. Uh-huh. Well, I will wait for at least 2 votes. D? Okay, so we have 1 vote. Okay?
How did you?
And?
No, say one of them said D.
Alright, so we have
Isn't it
A,
C?
right?
Huh? Isn't it C?
So the correct answer is C.
Yeah.
Alright? So
You know why?
it's okay.
You know
It's
why?
not
Yes, I know.
Say down, say why is C?
Why the answer is C? Well, if you remember
Because there's current
this
going through the
equation,
wire.
okay, the force equation,
There's magnetic force also
which
acting on
is
it.
E times your electric field, and then
just don't understand what you said.
magnetic force is
Or whatever.
Q B cross.
You just need to like reading from the notes.
So now, this Q is inverted, yeah, to negative sign. Then obviously the direction flip. Okay? So for both electric and the magnetic forces, where negative charge is positive charge will change the direction of the forces, right? Now I have another question. So now which one is true? So force exerted on a moving charged object can be zero. So is it going to be true for electric force or magnetic
electric. Yeah.
Refer to A, B, C, or D.
I would say A.
Both. Okay, so we have one vote for both. So
A.
let's wait for one more vote.
I say A. Say A.
Uh-huh. Don't be shy. We'll go up with the awesome answer. What do you think?
See, don't be shy.
What you want to see?
B. Okay. So we have answer for B. Alright. So the correct answer is actually B. Alright? Because again, if you use your equation for the magnetic force, then we have this velocity term here, and then what is this vector product? This is your V, and then magnetic field times sine, etc. Isn't it? So when the angle is 0 or 180, your force becomes 0. So you can have 0 magnetic force, even you have a magnetic field and then moving charge. Okay? Now I have one last question. I think this is the last question. Yeah. So a charged particle is traveling through a uniform magnetic field, and which of the following statements are true of the magnetic field? So there may be more than one correct statement. So well, I'm going to wait for 3 votes there. Okay, because we have more than one correct statement. So you can start voting now, yeah.
Here, you for.
So 1, 2, 3, 4, 5.
Yeah. I think got more than one. Sorry.
Guessing game. What's the answer there? What do you think?
I'm thinking.
Okay. Wait.
So tell me your thought. So what do you think is the correct answer?
C.
C. Okay.
You got me.
So 2 more votes to go. Alright?
Okay, so I say
Oh,
there.
alright. And one more. Your last chance.
What's the answer then?
Got 3. What's the last one?
Uh-huh. You can vote for the same answer, yeah? So one more vote.
2.
2. Alright? So the correct answer is 4 and 5. Right? So,
5.
again, I'm going to use the equation, or I will write down the equation.
Write down the equation.
So here, you can see that, you remember this right angular, yeah? So, your force is always perpendicular to the velocity and this magnetic field. Okay, if you remember this right angular, yeah? Your force is always perpendicular to the velocity and the magnetic field. Alright? So, well, because we have this vector product, so force is always perpendicular to the velocity and the magnetic field, so those first 2 answers cannot stand, alright? Now, we have the next statement which says that the magnetic force can increase the kinetic energy of the particle. So, in order to increase the kinetic energy, this force must change its velocity. Okay, because our kinetic energy is 1 over 2 mv squared. Okay, we are not going to increase this mass, but we can increase the velocity, yeah? But then, because the force is again perpendicular to this velocity, and then we know that when this force is acting on this charge, then this will push it, yeah? So it will make this motion. In other words, the force can change the direction, okay, the direction of this moving charge, but it's not going to add velocity or reduce the velocity. Okay, so we cannot accelerate. Alright? So the force does not change the velocity, therefore 3 also does not stand. And then we know that this force is perpendicular to the motion, so this is true, and then it does not change the momentum. Momentum is mv on it, so again the velocity is constant. So the 5 is correct answer, yeah? Alright, so then I'm going to move on to the next topic, which is the Ampere's law. Alright, the next topic is all about the Ampere's law. So we start with the Biot-Savart law because this Biot-Savart law tells us how to find this magnetic field from current, okay, at a certain point of P. Alright, and then this is the equation for this Biot-Savart law, and then in your lecture slide and the lecture video, this equation, okay, is used to derive this equation. Okay, so derivation from this first equation to this final equation is already given in your lecture video, so I'm not going to touch it. Okay, so please watch your lecture video. So this equation found very handy because we can determine this magnetic field at a given this point, okay, at a given point when a straight wire is considered. Okay, so in other words, if a straight wire is given, we can find this magnetic field at any given point, okay, using this equation. Alright, so that's why this equation is handy. So our the Ampere's law also uses the right hand rule. So I'm going to align my thumb to the direction of this current, okay, and then I'll just wind up the other 4 fingers. Then you know that my magnetic field direction is determined, all right. And then here again, when I align my thumb to this current, and then while the other 4 fingers will be the magnetic field direction.
Hey, you got eraser?
Why?
I think I forgot to pack my
Now, with that knowledge, we now ready to talk about this Ampere's law, okay? And then in order to do that, I'm going to draw some diagram.
Okay. Sorry.
First of all, you know this this Gauss law, yeah? I want to remind you of the Gauss law. So when the point source is given, this point source will generate this electric field in it. And then, in order to determine total charge inside total charge of this point source, we introduce a Gaussian surface. Yeah, this is Gaussian surface. All right, and then the Gauss law states that the total charge inside this surface over epsilon 0 is actually your electric field and then the area. Okay, it's a closed surface. So we use this equation to find this charge or electric field. Okay, and then in the Ampere's law, we consider a wire or the current. So I am going to draw a wire, all right, carrying a current I1 to the right direction. Okay, let's assume that there's another current running carrying I2, and then we may have another current carrying I3 but to the other direction. Alright, and then I'm going to introduce a loop, okay, a loop, and okay, there is a difference between this loop and then this Gaussian surface. The difference is this is important to calculate, okay? So in the Gaussian surface, this Gaussian surface is actually in the same plane. Or I cannot say plane because this is three-dimensional. Yeah? So I want to say that this Gaussian surface actually cut across those electric field lines. Okay, so electric field line and the Gaussian surface actually they meet. Okay, but in the Ampere's law, when I define this loop is not perpendicular, but this loop does not touch this electric currents. So in other words, let's say that I have those currents, okay, wires, then my loop is determined this way. Does it make sense? It's not going to be like this. Okay, this is touching, yeah? This loop touch this wire. We don't consider this loop our loop is right. Okay, there is no touching, alright? Then I'm going to now, so this is my loop, and then I'm going to define a surface, okay, a surface which is attaching to this loop. This is a surface. Alright? Then, so this is the surface, alright? Then this Ampere's law states that the current, okay, the total current going through this surface. So these wires must go through this surface, so penetrate through the surface, okay? Penetrate through the surface, right? So the current times mu zero is actually the same as the magnetic field over d r. Okay? Or you can say ds. Okay, let's say ds to be consistent with your lecture notes. So ds states this circumference of your loop. Okay, so let me talk it again. So the total current going through this surface, okay? This current must penetrate through the surface, okay? This cannot stop, okay? It must penetrate through the surface. This current is actually equivalent to our magnetic field, okay, around this loop. And then the loop and the surface are attached, they are attached to each other. So the way to visualize this loop and the surface is this. When I was young, yeah, so or younger, so I bring this, how do you call it, this insect catcher or whatever to catch those dragonfly or the butterfly, yeah. So you can find this in the supermarket as well, yeah. So it has this ring and then the net, yeah. So you can actually visualize this as this insect catcher or whatever. All right. So your current must go through the net, okay, and then your magnetic field is determined all around this loop, okay. So so we have this Amperian loop, and then Amperian loop, and then well, this is a two-dimensional diagram, so that's why I just draw the new diagram. Okay, so the way to see it, that there must be some area, okay, the surface, okay, which where this current actually going through. All right. So now we look at this and move on to this magnetic flux as in the Gaussian law. Okay. So magnetic flux is defined as this magnetic field times the area. So exactly the same definition as the electric flux. Okay. So your electric flux was E dot A. The same, yeah, the same definition, yeah. And then this magnetic flux is going to add this Tesla times meter square unit, and then which is Weber, right? Now, in the next slide, we have something called Gauss law in the magnetism. Okay, which might be a bit confusing because now you find that this magnetic flux is zero, always in the magnetism. Then what's the point of defining this magnetic flux if it's always zero? Okay, so then what's the point of having, well, what's point of defining this flux, which is going to be always 0. So in order to answer to that question, you may want to find the difference between this diagram and this diagram. Can you spot the difference between those two diagrams? So this diagram and then this diagram. What's the difference? Right? So the difference is, again, the definition of your drawing, your surface. So when we consider this Gauss law in the magnetism, your surface over your closed area is actually defined as this. In other words, this surface actually cross-cutting your magnetic field, as in the electric field of Gauss law. Okay, in the Gauss law, we define this Gaussian surface, and this Gaussian surface actually cut close this field. Yeah, they intersect with the field. Similarly, in this magnetism, okay, so this surface actually intersect with those fields. Then the number of influx and the number of outflux the same. Therefore, this magnetic flux is going to be always 0. Alright? However, in the previous slide, our diagram, as you can see here, this magnetic flux does not cross this surface. So in other words, this is our magnetic field, and then the surface is defined as this. Alright? So there is no crossing. Therefore, we can have a certain value. Okay? So that's the difference, okay? So don't be confused, and then don't jump that always this is 0. It's not. It depends on your surface, okay? So then we have another important concept, which is the displacement current. And then, unfortunately, we don't have a tutorial question, okay, that need a displacement current, okay, to solve. So what I'm going to do is, this displacement current is still very important concept. Okay, this is the final missing piece to complete the Maxwell's equation. So I'm going to introduce this displacement current in the next week. Okay, although we don't have any clear question related to the displacement current, but this is very important concept. So that's why I want to introduce this concept next week. All right. So well, I will leave those to next week. So we can start with the question. Do you have any questions so far? Alright, so then let's start. So question 1. A uniform magnetic field of 0.15 Pascal is directed along the positive x-axis. A positron, which is similar to the electron but having a positive charge instead of negative charge, moving with the speed of this, alright, enters the field along a direction that makes an angle of 85 degrees with the x-axis. Now we want to determine the pitch radius of the trajectory. So this diagram is not very useful, okay, to determine the pitch and then radius. So I'm going to draw a new diagram, alright, with my x-axis, okay, as a horizontal line. Then I have y-axis, and then z-axis, alright. And then magnetic field is defined along this x-axis. And then a moving charge is injected to this magnetic field at this angle. Okay, so this is our velocity, and then this velocity has an angle of 85 degrees with the x-axis. Okay, and then we know what would happen to this moving charge particle. Well, it's going to make this a helical motion. Yeah? So I'm going to draw a helical motion. Alright. constant speed because the force acting along the x-axis is zero. Alright? So our pitch, okay, pitch of this angular motion is going to defined along the x-axis, and then this pitch is going to be the same, okay, along this x-axis because it travels at the same speed, it's a constant speed. So I'm going to define p here, alright? Then my p is going to be the speed, okay, times the temporal period, right? And then your temporal, so because this is the distance, okay? Because this is distance, yeah? The distance is the speed times the time, yeah? So now, this pitch is determined along the x-axis. So in other words, I'm going to use only the x component of the velocity, okay? Because the y and z component are not, they do not contribute to this. So then my x component is easy to determine. Yeah? When you look at this diagram, the angle between the velocity to the x-axis is already given. So Vx. So Vx is actually the projection of this velocity onto this x-axis. Yeah? So this is going to be 3 times cosine 85 degrees. And then we need to determine this temporal period. And then temporal period actually was determined earlier in the slide, yeah? So we just use this relation. So I dropped this vector notation for this magnetic field because we already know this direction, okay? So I just dropped that. This is Q, V, E, and then this is the centrifugal force, which is mv squared over r. Alright, so my radius now becomes mv squared of qvb, which is mv over qb. Alright, and then we know that our temporal period is 2 pi r over hg. So I just substitute this in this equation, and this becomes 2 pi v times mv qb. The speed will go away, we will left with 2 pi m or q. Okay, so the mass of the positron is given in the list of the constant, and then charge also given in the list of the constant, and then the magnetic field is given in the fraction. So you can actually solve this, okay, for this temporal period. And then you are going to substitute this into the pitch to determine the pitch, yeah? Now we want to determine the radius of the trajectory. So in other words, we want to find the radius of this helical motion. And because this three-dimensional helical motion, so it might be a bit difficult to digest, okay, this radius. But we know that, we already know that this helical motion actually have two motions, okay? It's made of two motions. The first motion is the constant traveling along the x-axis, and then the second motion was the circular movement, okay? On the y-z plane, so we have circular movement on the y-z plane. And then your radius is going to be defined. Does it make sense? Yeah? Your radius is going to be determined on your y-z plane. Alright? If you look at from this direction, you are going to see only this circular movement, yeah? On the y-z plane. So the radius is going to be determined in the y-z plane. So in other words, I'm going to use this equation, okay? So my radius is mv over qb. And then, what about this velocity? Right, we don't worry about this x component anymore because this circular motion is on the y-z plane, and this radius can be expressed in terms of the y component as well as z component because the radius is always the same, yeah, always the same when the circle is given. So radius can be were expressed in terms of y or in terms of z, and then I'm going to use this y component simply because 85 degree is given. Alright, so in other words, this is going to be 5 degrees, or the projection of the velocity on this, okay, Vy is going to be 3 times sine 85 degrees, or 3 times cosine 5 degrees. Okay, sorry. Alright? So, because the angle is already given, I'm going to choose this y component, and then my equation is going to be, so it's y, n times 3 sine 85 degree over qb. Alright, so again, when all these constants can be found in the list of constants or in the question, so you can actually solve this for the radius, yeah? So I'm going to show you my working. So this pitch, which is a traveling distance along the x-axis, is actually the speed times the temporal period. And then from those three equations, we can find this temporal period. And then therefore my pitch is determined as this, right? And then to find this radius of the trajectory, we know that this radius is defined inside this y plane, so we use a y component because the angle is given, so it's determined as this. Alright? Now I'm going to move on to the next question. So a velocity filter has an electric and a magnetic field directed as shown. The magnetic magnitude of the magnetic field is given by this, right? And then we want to find the magnitude of the electric field such that 750 electron volts electrons entering the filter will not be reflected. So
You know how to do
No.
concentration.
we are given this velocity filter, okay, and then in the velocity filter, the electric field and the magnetic field,
Black
they
bear.
exist
Wait,
together,
what are
okay?
black shirt?
So our electric
Hey
field,
Kang, do you get new shoes?
okay, so our electric field is determined along this
Sorry, I thought
direction. So
your
this
shoes
is
look
our
so
electric
spongy.
field.
Spongy.
And then our magnetic field is determined, okay, it's given as this, okay, going into A.
Why
So
are you wearing a sweater?
from this, let's first, so we have electric field and the magnetic field. In other words, we are going to build a Lorentz force, okay? Lorentz force, which states that Q E plus P velocity plus magnetic field. So when we want this electron fired from this source will travel at a straight line. Okay? Without any deflection. So in other words, this Lorentz force must be 0. Okay? So then this electron won't feel any force exerted on it, therefore it will just travel freely, okay? So what we have to do is we first need to determine the direction of this electric force and then direction of the magnetic force. Alright, so let's first determine those forces. So what would be the direction of the electric force? So what's the direction of the electric force? So what should be the force direction? Electric field, the direction is already given, yeah? So what's the force direction? Down, up, left, right.
Downwards. You know why?
Uh-huh.
Downwards.
Now, well, your force
Downwards is it?
is Q times electric field, yeah? So your force and the electric field are actually parallel, aligned. Only if your charge is positive. Now here, we consider electron whose charge is negative. Okay, so we have this negative sign here. So in other words, the force and the electron, they are in the opposite direction. Does it make sense? So electric field is actually pointing over. Okay? So, in order to have zero Lorentz force, our magnetic force must direct
Say
it
up.
downward.
You say down.
Okay, so
He said
we are going to
electric force is
use
down, magnetic
right
force
hand
up.
rule,
Is it correct?
okay, to
Magnetic force is up,
determine
electric force
is
is
the
down.
magnetic force
I can't hear
direction.
you.
Electric force is down,
Okay,
but magnetic force
and
is up.
then the
No, he said
magnetic
magnetic
field
up,
direction
also.
and then
Because
velocity
equilibrium,
direction
I mean, he
is
don't want
all
the-
given in the
the
question.
question to
So
not be
let's
tested.
practice this. So please use right hand rule and then see whether you can determine his force direction, magnetic force direction downward. Okay, let's start. Use your right hand rule. Alright?
You know. Is it pushing? Which one you do?
Current, magic.
Current.
Isn't the middle finger current?
Middle finger is FU.
Show me any like pretend I'm doing something. Pass me the Come on.
2. Where do you even come?
Record video only.
I can record for you.
Not 7, 2 people.
Is it how you are learning at the same time? Not
No, I
like
never even watch a video. You know what I did? Like shook. You cannot shook, bro.
Correct, it is. Right, then magnetic field voltage, then falls upwards.
That's right hand grip rule, right?
No, but no, as in, but then I do it.
Yeah, you can use
right,
right
but I used to do this.
Yeah, you can use right hand grip. Both the same.
It's not right grip rule, but it's like this one, like this.
It's right hand grip.
It's not,
rule.
right hand grip is
Dr.
like-
Who says right hand grip rule.
It's not, it's different.
Then what is this called? Yeah.
This is just the right hand rule, but then it's just a different style.
But we need